Okay, kids, we're back. Section 3.2, practice question 6. Now, kids, this section is about something called universal gravitation. This works anywhere in the universe. This is not like the first section, 3.1, where we were only investigating the force of gravity on objects near the surface of the Earth. This works on the surface of the Earth, and it also works everywhere else. That's why it's universal. This is mostly used for finding the force of gravity between large heavenly celestial bodies, right? The sun and the Earth. What's the force of gravity between the sun and the Earth? Because if there's no force of gravity between the sun and the Earth is not going to stay in orbit around the sun. We'd be in trouble. The moon around the Earth, right? What is keeping the moon zipping around the Earth for these 5 billion years? Well, gravity. So that's universal gravitation. And there's an equation for it. And look, the symbol changes. It's no longer F little g, right? It's F big G. Okay? So what does it equal? There's an equation for it. It equals, in the numerator, the mass of the two objects that are having a gravitational attraction. It could be the Earth and the moon, right? The Earth and the sun, whatever. How far apart are they squared in the denominator, right? And by the way, that distance between two objects, right, is always center to center distance, always, okay? And then there is a very special number that makes all of this work, big G. It's the universal gravitational constant. See, it's got a very specific name. The universal gravitational constant. And it is equal to 6.67 times 10 to the negative 11 newtons meter squared all over kilogram squared. So, what do we know? We know that when this object right here, when that object right there is on the surface of the Earth, we know what the universal gravitational force is. We know the magnitude of it. It's 634 newtons. Okay? So I can combine these two and say, in situation, oh, come on now, don't be like this. Don't start doing this. In situation number one, when the object is on the surface of the Earth, we know that this is equal to 634 newtons, and it would equal big G. The mass of this object is what is this? An astronaut. The mass of the astronaut times mass of the Earth, because those are the two objects that are involved, right? Those are the two objects that are pulling on each other, gravitationally speaking, divided by how far apart they are center to center. Well, the distance that they are center to center, if you take a look at this diagram, oh my goodness, why is it doing that? If you take a look at this diagram right there, distance from one object to the other, distance 1, 2, basically, for all intents and purposes, we can say, look, this distance right here is so close to being the radius of the Earth, let's just call it the radius of the Earth. If you add a meter, because you've got to get to the belly of the astronaut, what's a meter going to change when we're looking at the radius of the Earth? Nothing. Okay? So for all intents and purposes, that distance d1 is just the radius of the Earth, and that is squared. Okay, so that is equal to the force of gravity using the universal equation between the astronaut and the Earth when the astronaut is on the surface of the Earth. But now they say, hey, you know this. You know this. It's 634 newtons. You know this. What would be the force of gravity on the object, the astronaut? So here's the Earth. If now the astronaut is no longer on the surface of the Earth, but now, and I'm going to pick one of them, I'll pick B, okay? Now the center to center distance between the Earth and the astronaut, right? This distance between the two objects, distance from 1 to 2, is no longer the radius of the Earth. It is 5 times the radius of the Earth. What's the force of gravity now using the universal equation? Well, I don't know. Let's find out. So we would say, okay, and we're only interested in the magnitude. Force of gravity in this second situation. Look how I'm calling it force of gravity number 2. This is the second situation, all right, is equal to big G, the universal gravitational constant. Well, what are the two objects involved? Well, that hasn't changed. Mass of the astronaut, mass of the Earth, so those two are in the numerator. So we've got 3 things in the numerator, divided by the distance between them squared. Well, the distance is now 5 radius of the Earth. It's no longer the radius of the Earth, it's 5 of them. So I have to square the entire thing. Okay? You need to focus. Okay, well, let's continue here. Let's see what mathematical magic we can do here. Well, this is equal to, I don't know why it's doing that, but whatever. Kind of weird. There we go. This is equal to, look, I pushed down the green. Look, green, there we go. This is equal to G, mass of the astronaut, mass of the Earth. Let's do the math. Let's do the squaring. Okay? Well, if I square a 5, I get 25. If I square radius of the Earth, I get radius of the Earth squared. Well, I don't know if you know this, kids, but dividing by 25 is the same as multiplying by 1/25. That's like saying dividing by 2 is the same as multiplying by a half. Dividing by 3 is the same as multiplying by a third. Are you guys okay with that? So I'm going to rewrite this as 1/25 of this expression. Don't be like that. Don't be like that. There you go. Okay? It's 1/25 of that. But kids, have we not seen what's in the bracket before? Have we not seen that somewhere else? We have. Look. Right here. It is actually force of gravity 1. So this is saying the magnitude of the force of gravity on the astronaut in the second situation, when he or she is 5 times the radius of the Earth away from the center of the Earth, is 1/25 of force of gravity 1. Okay? 1/25 of your 634 newtons. It's literally equal to 1/25 of your 634 newtons. Now, let me tell you something about this, because this is a big step for some of you. This is called solving by mathematical reasoning. Okay, so what did we do here? this is what we did. We came up with an equation. Here it is. Look at it. Here's the equation for situation number 1. Then I came up with an equation for situation, oh, don't be like that. I came up with an equation for situation 2. There it is. And I needed an equation to link these two. And the equation to link these two was that the distance in the second situation was 5 times the distance in the first situation. So you needed an equation to link the two of them. And as you move on in science, physics, chemistry, mathematics, you'll see more questions like this, okay? Where you've got to set up a situation, write down equations that work in that situation, set up a second situation, write down equations that work for that situation, right? And then find something that will bring them together. In this case, the thing that brought them together is we knew that the second situation involved a distance that was 5 times the first situation. How can I link the two? And then come up with an equation for that. As you do more and more studies in this, you'll see more and more of these mathematical reasoning questions. Did that help you? Okay. Bye, kids.